All right, so by the end of the day today, that first Connect and first Excel assignment are due. I had a lot of people reach out for questions, things like that. I'll be available kind of this afternoon, but if you send me something after 5, I can't guarantee I'll get you the quickest email. So we're gonna jump in to what we had just kind of introduced last class, which was, here we go, kind of this idea of using Bayes' theorem. So we had these setups where we had two states of nature. So maybe this is guilty, not guilty, HIV positive, HIV negative, pregnant, not pregnant, right? Either one of these two is the true underlying state of nature. Now, we want to know which one it is, right? Oh, sorry. And so if these are the only two possible outcomes, right, I'm either guilty or I'm not guilty, right? In the sense that that's not what a jury finds me, but that's true. I've either committed the crime or I haven't. If those are the only two outcomes, those probabilities have to add up to 1, right? Anytime we add up the probability of all the experimental outcomes, they should add up to 1. Right? And we can't really observe this state of nature directly, right? I can't truly know if someone's guilty or not guilty, right? But I can run some test, right? Or I don't truly know if they have a disease or if they don't by looking at them. So I run this test, right? These tests aren't perfect. So, even if it comes back positive, it's not 100% that the person has the disease, right? Or if I see it come back negative, it's not 100% that they don't have the disease. So what we're going to do is use the outcome of that test, so E, or E complement, I guess, if positive or negative. Whatever the outcome of that test is, we then want to say, okay, given that I've seen that outcome on the test, what's the probability that the true state of nature is what the test indicated, right? Given that I see a positive test result, what is the probability that they actually have the disease? Okay? And we'll give a couple examples to this, but this is the general setup, right? And kind of think about whatever disease we're interested in. So I think I'll go through an HIV example today. Hopefully I'll have time at the end of class, or towards the end of class, we'll do something kind of fun, I think, with, say, fun, time, relevant to the times with some COVID data. So the general equation we would use to find a conditional probability is the intersection of two events divided by whatever I'm conditioning on. Okay? Now the problem is the probability of E is just a probability that the test comes back positive. Well, the probability that the test comes back positive depends on how many people actually say have that disease. If half the population has the disease, well, the probability that test comes back positive will be a lot higher than if only 1% does. So we don't really have a direct probability for this, and we're gonna have to break it down to some different components, okay? So one thing that we know is that the intersection of two events can be rewritten as the conditional probability times what we're conditioning on, right? So if we're gonna wanna rewrite this intersection in our numerator, we can rewrite that as a conditional probability times the probability of what we're conditioning on. Okay? So that's kind of the first step. It's just we're using that multiplication rule. The second step is a little bit kind of, I'll explain with intuition. So if I want the probability that somebody gets a positive test result, well, that's going to be composed of two types of people. People who get that E, that positive test result, and the true state of nature is they have the disease. But it's also going to be made up of this second group, which is people that get a positive test result and don't have the disease, right? Or these false positives. So to get the probability that, I see a positive test, I'm going to have two types of people in that group. People who got a positive test result and have the disease, people who get a positive test result and didn't have the disease. Okay? With that in mind, I can rewrite these intersections as conditional probabilities times whatever I'm conditioning on. Now notice here I'm conditioning on different things, right? Because this group doesn't have the disease, or the state of nature is state of nature 2, and this group does have the disease or state of nature 1. So I'm just rewriting things using my multiplication rule. Well, now I can plug this in to my numerator. I now have something I can plug in for the probability of E into my denominator, and I come up with this kind of longer lengthy equation. And why do we have to kind of go from this to this? Well, we just we don't have this information directly given to us. A lot of the time, especially when we're looking at these testing things, we have conditional probabilities, but we don't have kind of the probability that we just see the outcome of the test be a certain thing, right? And you can kind of see here, you know, I'm, oops, there we go. Kind of using these, plugging these things into this formula to arrive here, right? So if we know that we can find this conditional probability that we might be interested in using this equation, what's that going to look like, right? So a couple more things to talk about before we look at our first example. We already talked about the probability of the states of nature have to add up to 1. But here, if we condition on the same state of nature, so if these are both S1 or these are both S2, the conditional probability of the two outcomes of the test, E and E complement, have to add to 1. So think about it this way. Given that I'm looking at somebody who has the disease, the probability they get a positive test result, let's say it's 40% or a probability of 0.4. Well, given that they have the disease, then what's the probability they didn't get a positive test result or they got a negative result? Well, it's just the remaining 0.6, right? There's only two outcomes that that person could see. So once I'm looking at the same kind of person, right, the same state of nature, the probability, the conditional probability of the two outcomes of the test, those should also add up to 1. Okay? And then if we condition on different states of nature, these conditional probabilities don't have to add to anything, right? All bets are off. We don't know what these are going to be, right? So the only time that we know those conditional probabilities of the two outcomes of the test add to 1 is when we're conditioning on the same state of nature. If we're conditioning on different states, we don't know what those probabilities will add up to. Excuse me. All right. So let's go back to kind of this HIV test example that I gave in the original slide. So if we go out and collect information, what we'll find is, that, you know, out of, if you were to choose any one American at random today, the probability they have HIV is 0.006, or about, you know, 0.6% of the population has it. Okay. Whoops. The probability that an HIV test shows a positive result for a person with HIV is 0.999. Or given that someone is HIV positive, the probability we see a positive test result is 0.999. So we'll start writing these out and just thinking about what we have. So I'm going to try something here as we go through this today. See if I can make this as big as possible. All right, there we go. I'm going to stop share real quick and switch my video over to this guy if I turn it on. Hopefully it pops up here in a second. Maybe. Let's try doing it the other way. Whoa. There we go. All right. So if you're on the Zoom, I'm sharing my screen, but kind of also have the video pulled up. I'll kind of be going back and forth. So what we've really been given up to this point is the probability that if we chose someone at random, the probability they have HIV is 0.006, right? So let's just start writing these probabilities down. If the probability that someone is HIV positive is 0.006, what's the probability that someone's HIV negative? So if the probability that someone is HIV positive is 0.006, the probability that they're HIV negative would be what? Yeah. Yeah, it's the two states of nature. We know those probabilities have to add up to 1. So I could just subtract the probability of being HIV positive from 1 and get the probability that they're HIV negative. The next piece of information I was given was the probability that, given that the test kind of shows a positive result. Nope, I'm sorry. Ignore that. Given that somebody is HIV positive, the probability we see a positive test result, right, is 0.999. Okay. Now, if I think about this, if I know that given that someone has the disease, the probability they get a positive test result is 0.999, well then given that they have the disease, what's the probability they get a negative test result? Well, if we think about that, we don't have any inconclusives here. We have a definitive test. These are the only two outcomes. So the probability, if we condition on the same state of nature, right? Think about this as our S1. Our outcome of the test E and E complement, these probabilities have to add up to 1. So even though we weren't directly given it, we can figure out what that conditional probability is as well. Okay. Any questions on that before we keep moving? All right. Then the final thing that we're given here is the probability we see a positive test result for an individual that's HIV negative is 0.01. So up here, what I'm thinking about there is, given that someone is HIV negative, right, they don't have the disease, well, then the probability we see a positive test result, not 0.99, much, much lower, it's only going to be 0.01. Okay. And then think about it here. If this is our second state of nature, if we condition on that same state of nature, S2, what's the probability we see the other outcome of the test, or that the test shows negative? Well, if there's a 1% chance that the test comes back positive for someone who's HIV negative, then the probability that they see a negative test result if they're HIV negative would just be whatever gets us to 1, right? Those two outcomes of the test, conditioning on the same state of nature, these have to add up to 1. So if we knew one of these, we could find the other in any of these sets, right? So we really only given, I think, we were given this, this, and this directly, and we, from that, could derive the other three probabilities. Okay? Any questions on that, or I'm not sure what you're viewing on and how small the writing is here for you, depending on what device you're on in Zoom, but. Oh, shoot, you guys can't see. Sorry for those of you guys in class. I mean, you got all those, but I was kind of working off of this slide. We'll see if this, hopefully this pops up for us in a second. There we go. All right, so we were just kind of, from this information, deriving all three. Oh, you could see that, those three probabilities, and we found the other one. So another way you could think about this, and we'll come back to this question in a second, but another way you could think about this is you could set this up like a tree, right? So here's your state of nature 1, here's your state of nature 2. You were only given this, but you know that this row of the tree or whatever have to add up to 1, right? So once you knew one of them, you automatically knew the other. Then over here on this branch, I'm going to be conditioning on this state of nature. So I condition on being HIV positive. The probability I see these two outcomes, a positive or a negative test, I know these probabilities have to add up to 1. And I was given this one, so I could then derive that. And then over here on this branch, I'm going to condition on the state of nature that's on this side of the branch, HIV negative. And the probability of the two outcomes of the tests, these would add up to 1. So it's like this row adds up to 1, this branch over here, these add up to 1, and this branch over here, these add up to 1. Okay? And you don't always have to set this up, but if you did, you could answer any question. So I think the question we start out with here, let's identify the probability we're looking for. So if the test is administered to a random person and it comes back positive, what's the probability the person actually has the disease? Okay. So here, what we're looking for, the question is actually saying, what's the probability that the person has HIV? So what's the probability that someone is HIV positive, given something that we've seen, which is that the test came back positive. Right? Oh, sorry. There you go. So this is what we're looking for, given that we see this outcome on the test. So we could think about it, here's our S1, and here's the outcome of the test we're interested in E. Okay. So what we're going to do is we're going to go back, right? Oh, sorry. So we're going to go back and look at that general form of the equation and just write it out, and everywhere we see S1, let's go back here. Let's get the colors off here for a second. Everywhere we see S1, we'll just write the probability of being HIV positive. Everywhere we see an E, we'll write that the test comes back positive. If our S1, or state of nature 1, is HIV positive, then what would our state of nature 2 be? Yeah, just being HIV negative, right? Those are the only two states of nature. You either have the disease or you don't. So if we were just to use that equation, right, we've already done the following steps, right? We identified the probability of what we're looking for. We had all those probabilities written down earlier, right? We actually had more than this, but these are the only ones that were directly given to us. We're just going to write that formula out, and like I said, plug in our state of nature, S1 and S2, plug in the outcome of the test we're looking at, E, write out this in the context of our example, and now it's just a matter of plugging things in. The probability someone's HIV positive is that 0.006 we had. The probability that given they're HIV positive, the test comes back positive, that was something else that we identified. So I plug those in, probability someone's HIV negative, 0.994. Given they're HIV negative, the probability we see a positive test result, 0.01. So it's just a matter of plugging all those values in. We'd end up with something like this, right? Now it's just a matter of getting that entered into our calculator, right? I mean, 0.006 times, I mean, this is division and multiplication and addition. This shouldn't be too bad once we have our numbers plugged in. Okay? Now the interesting thing here is a little bit counterintuitive, is that the probability that if you see a positive test result, the probability that someone is HIV positive is only what, 38%, or probably 0.38. So why is that so low? Is that just saying that these tests are really bad? Well, no, the test was really good, right? That 0.999 was that if I had the disease, the test identified it at a very high rate. The issue is the false positive rate, right? People who didn't have the disease, about 1% of them were seeing a positive result there. So anytime we have, excuse me, anytime we have probabilities, another way we can think about this is frequencies, okay? So one thing that we thought about last class was building those contingency tables. How did we get those probabilities? We were really just taking frequencies and dividing it by the total number of observations. So let's think about these probabilities. We can also intuitively think about them as numbers, right? As frequencies, if we just kind of remove that divided by the total number of observations part. So I'll try to break this down. So using those percentages that we had, about 0.006% of the US population has HIV. I'm going to round the numbers a little bit here, but you get the idea. If they change a little bit, this would be work nice. But I'm just going to change them so the math is easy. Let's say that there's approximately 300 million people in the US, right? I know it's a little bit higher, but it's a good round number for us. If 0.6% of them have HIV, right? We'll use 0.5 because the math's a little bit easier and it'll be around the same number. So 1% of 300 million is 3 million. Half of that, right? 0.5% would be 1.5 million people in the US will have HIV. That test was 99.9% accurate at identifying those individuals. So if we multiplied this by how accurate the test was, we're still going to have about 1.5 million, right? Just a little shy, okay? So there's approximately 1.5 million people who are going to have HIV, and they'll get a positive test result, right? The other 99.5% of people who don't have HIV, right? That's going to be just shy of 300 million people, right? Well, the false positive rate was 1%. So 1% of almost 300, well, I guess it would technically be what am I saying, 98.5%. Yeah, it's going to be just shy of 300. 1% of that is going to be approximately, right? It's going to be a little bit lower, but approximately 3 million people are going to have the disease, not have the disease, but have a positive test result, right? Those false positives. So these are going to be people that are HIV negative, but they had a false positive, right? So now you've got 4.5 million people sitting around with positive test results. So now if I come to you and say, hey, look, this person got a positive test result, you don't have any other information about them, what's the probability they actually have the disease? Well, there's 4.5 million people with the disease. I know that only 1.5 million of them actually have it, right? There's 3 million without it, 1.5 with it. So the probability that if I see a positive test result, I've got these 4.5 million people who would have a positive test result, only 1.5 million of them actually have the disease, so this would be my probability. So this is roughly, 33%. With the actual numbers, because I was rounding a lot here, we ended up finding it was actually 0.38, right? Because I rounded my numbers pretty roughly here. But the idea is that what we're really trying to do with this Bayes theorem is we know there's 2 types of people that are going to see the outcome of that test. Some, the positive test results. Some of them won't have the disease, the false positives. Some of them will, right? The correct positives, so we want to think about it that way. Okay. Any questions on this before we keep moving? I don't want to run out of time for that example because I think it's fun, but we'll go back here. So we'll go through another example. It's a little bit goofy, but we can make some connections to some pretty applicable stuff, right? So let's say I have this truth serum, and it makes people, my goal is I don't want to have to use juries anymore. I want to have this drug that makes people confess to crimes, right? But I'm working on it, and it's not very accurate, right? Yeah. So given that someone's innocent, it incorrectly changes them to confess or say they're guilty about 1% of the time. The probability that if someone's guilty, that this truth serum essentially doesn't work and they still claim their innocence is about 10% of the time. Okay? So we've got these 2 conditional probabilities. We're then told, and here I think I have a grammatical error that I just need a comma here so this makes a little more sense. Okay. If 5% of suspects that are brought in are guilty, so here we're going to think about this as the probability that the state of nature is guilty is 0.05. Okay? So the probability that someone is guilty, or the state of nature is guilty, is 0.05, which means the probability that they're innocent would be what? With no additional information, probably they're guilty is 5%, the probability they're innocent should be just, I'm either innocent or I'm guilty, right? Those are my 2 states of nature.
0.95.
95%, exactly, yep. So the probability they're guilty is 0.05, probably they're innocent, 0.95. So now if the truth serum indicates guilty, what's the probability that the person is actually innocent? So what we're looking for here, right? Let's identify first what we're looking for. So it's given that the truth serum kind of indicates that they're guilty. What's the probability they're actually innocent, right? And you could shorthand this, I don't know, and use like I and G here if we wanted to kind of make it a little bit easier, but that's what we're looking for, right? So what was given to us in the problem, we already talked about the probability they're innocent and the probability they're guilty, and then those 2 conditional probabilities, which were easier to identify, they were directly given to us, not in words, right? So this is what we're going to have. We're going to have to go back and use Bayes' equation to write this out in the context of our example. So I'll show you how we do this. I think this will help. Let me see if I can get to that formula. Oops. All right. So we've got that general form of the equation down there. Right? So this was my outcome of the test E. And here's my state of nature 1. Right? So I'm just going to write out this formula in the context of my example. So the probability of S1 would be the probability that someone's innocent times the probability of E given S1. Well, my E is that the truth serum makes them say they're guilty. I'm going to kind of shorthand this with just a G here. Given S1, so that was that they're innocent, divided by, notice the first part of my denominator is the exact same as the numerator here, right? So I can actually just rewrite that It's the exact same thing I have up above. So probably they're innocent times probability that truth serum makes them say they're guilty, given they're innocent. Add in, right? I'm going to run out of room here, but the second state of nature is what? The probability that they're guilty, right? If my state of nature 1 is that they're innocent, my second state of nature that I'm plugging in here is that they're guilty. Times the probability of E, which my E was that they're guilty, given S2, which is that, so the truth serum makes them say they're guilty, given that they are guilty. I know this is a little hard to read. I ran out of some room here. Okay.
So you wouldn't be able to.
So all I did there was try to reproduce this general equation in the context of my example. So maybe a little bit cleaner. I just want to show you that so you can kind of see how you would do that. Right, once we had what we were looking for, innocent, and the truth serum made them say they're guilty, we wrote this out in the context of our example. So here everything's abbreviated with guilty and innocent is just G and I, which is probably in hindsight what I should have done here. I wouldn't have ran out of his room as quickly, but I wanted to kind of show you the process of just substituting in there your S and your E, okay? Now the issue becomes, when I start to go to plug things in here, I have the probability that they're innocent is 0.95. Given they're innocent, the probability that truth serum makes them say they're guilty is 0.01. The probability someone is guilty is 0.05. But I wasn't directly given the conditional probability of, given that someone's guilty, what's the probability the truth serum made them say they're guilty, right? I don't have that. But notice, I do have something that's conditioned on the same state of nature. So if given that someone's guilty, so think about it as I'm telling you, you know this person's guilty, and the probability a guilty person still says they're innocent after taking the truth serum is 0.1. Well, what's the probability that person, the truth serum makes them say they're guilty? Well, yeah, it's the other 90% of the time, or probability of 0.9, right? Oops. How'd you do that? Well, you know that if we condition on the same state of nature here, the probability of the two outcomes of the test have to add up to 1. So 0.1, what would it get me up to 1? 0.9, right? Or 1 minus 0.1 is 0.9. We plug that in, and now we've got everything we need, right? Now, if we would have written this out like I did in the previous example, or using one of those, like drawing those probability trees, then I would have had that already, right? But in this one, I didn't do that. I just was using what I was given, and then when I got stuck, then I used that rule and kind of derived that 0.9 for the probability I didn't know.
So you can't like cancel out the numerator with the beginning of the denominator?
Yeah, so you're asking, can I cancel out this guy with this right here?
Yeah.
For the same thing?
Yeah.
So I can't, right? Because, if I think about, the only time I can cancel something where I've like added is if I'm dividing everything by the same. So here I've got two components of my denominator. So let me try to give you a quick example why we can't do that. So if I've got 10 divided by 5 plus 5, right? What should this be? 10 divided by 10 should be 1, right? But if I try to cancel this, right, I'm going to end up like thinking this cancels. And then, or if I thought that I could do this so that it's 2 plus 10 over 5, and that ends up 4, right? We know that that's not right. So you can't cancel something unless it's something like this, where you're dividing kind of something that you're adding by the same value. Then you kind of know this is 1 and this is 1. So you could say like this is actually 1 plus 1, which is 2, which sure enough, this ends up being 2 as well. So anytime you're adding things in the denominator, you can't just cancel out with what's in the numerator.
Okay.
Yep. All right. But a lot of people want to do that when you see that. That's not trust me, that's not an uncommon question. So going back to this example, where are we on time? Okay. So I use this example, once we plug the values in, we got about 0.17, right? So what is this really saying? Okay, so I know this is a goofy truth serum example, but let's just replace the truth serum with a jury, right? If the probability that given someone's guilty, the jury doesn't find them guilty, they only get it wrong 10% of the time. I don't know, I'd say that's pretty good. There's a lot of people that you think are guilty who end up being found innocent. And the probability that if someone's innocent, that they're incorrectly convicted is 1% of the time, right? These aren't wildly probably different than maybe what we see with a regular jury. We're just putting it in the context of a truth serum. Then what this is saying is that given that a jury found someone guilty, the probability they're innocent is only about, is actually as high as, 17%, right? And that's just because most people aren't guilty of crime or of crimes that involve long bouts in jail or so. It's just kind of an easy toy example. It's not using actual values, but, and I'll skip ahead and we'll come back to that in a second. We can think about just replacing that truth serum with the word jury. And this is a very applicable thing. Like given that the jury finds someone, oops, I didn't want to show that yet. Given that the jury finds someone guilty, what's the probability they're actually innocent? Like how many people in jail actually are innocent people, right? Well, you've got two groups, right? People who were found guilty and actually are innocent, but you also have people who are found guilty and actually are guilty, right? So hopefully that latter group, the group that was found guilty and actually are, hopefully there's more of them, right, than there are innocent people in prison. But what we can do is kind of go back now and say, given that someone was guilty, what's the probability the jury found them innocent? And given that someone was innocent, what's the probability that the jury found them guilty? By looking at past data on overturned court cases. So like there's a lot of cases, you got like the Innocence Project and all these things where using DNA evidence, there's a lot of cases that have been overturned. And you can get an idea about what percent of cases were juries getting incorrect, right? In both directions, okay? Once you obtain those conditional probabilities, you can start plugging those into this Bayes equation. We could actually derive like a value of like how much what percent of people in prison are actually innocent, right? So I had, right, the given that they're guilty, what's the probability that they're found innocent? And given that they're innocent, what's the probability they're found guilty, right? I'm not arguing that either one of these is definitive, just a kind of cultural reference here. We're thinking about these two groups, okay? All right, so I want to go back to this. So given that this truth serum, or we could think about it as a jury, indicates that someone's guilty, what's the probability that they're actually innocent? We found it was 0.174, okay? With that in mind, given the same setup, if the truth serum indicates guilty, what's the probability the suspect actually is guilty? So that what we found before was given that somebody was innocent, given that we saw the truth serum say they're guilty, what's the probability they're actually innocent? Now what we're looking for is, given that the truth serum says guilty, what's the probability that they're actually guilty? Well, just before, what we had found was given that the truth serum made them say they're guilty. This looks like a 6, not a G. Right, a G there. The probability they were innocent was about 0.174. Okay? So one thing I had said earlier was if we condition on the same state of nature, the probability of the two outcomes of the test have to add up to 1. But similarly, if we condition on the same outcome of the test E, the probabilities of the two states of nature, these would have to add up to 1 as well, right? Let's say I had a room, or let's say I looked at the entire country, right? I then single out only people that this truth serum made them confess to a crime. So of these people now, I'm only looking at people who said they were guilty of a crime. What's the probability they're actually innocent? Well, that was 0.174. So of that group of people, what's the probability they're actually guilty? Well, it's just the remaining people in the room, right? The ones that didn't say they're innocent. So if this conditional probability is 0.174, this would just be 1 minus that, or what, 0.826. Okay. So I could rewrite this entire thing out using Bayes' theorem again and plug in all my values, and I would find 0.826. But because I had this previous work done, where was it? There it is, right? And I know I'm conditioning on the same outcome of the test, the probability of the two states of nature I know will have to add up to 1. Okay? And I mean, it's kind of intuitive, right? Like, given that we're only looking at people that the jury or the truth serum made them say they're guilty, the probability they're guilty is 0.4, then the probability they're innocent has to be 0.6, right? They're either one or the other, right? So, but the kind of key there is conditioning on the same thing. The same thing on the right-hand side of that line. Any questions on that before we keep moving? I'll do one more example today. So, yeah, I don't know if we'll get to this today. We might save this for next week. So I'm going to base this off of some actual data. I pulled this open this morning. So this is, I forget, does it say where this is from on the side? This is in a peer-reviewed article. I don't know if it says on here. This was on the Lancet, but I looked this up on some other sources, and it seems to be pretty consistent with kind of the general findings in the academic world. So here I was looking at kind of curiosity of COVID tests, right? So at any one point in time, like if you look at like the current 7-day average, there's only about 0.5% of the population that has COVID, right? Concurrently, right? I think cumulatively over the last year, it's up to something like, I don't even know, 15 to 20%, somewhere in there. But at any one point in time, there's only about 0.5% of the population that has it. Okay? So if we look at kind of false negative rates, and this reports that in different studies, they've been anywhere from 2 to 33. I was looking at some other sources, and a lot of them kind of didn't have it as high as 33, but the general finding was around 2%. So we'll say that the false negative is 2%. And then, where was the other one? So was it over here? I think there was a 95% in there somewhere. Right, so the kind of how accurately they're identifying the positive cases. So given that someone has it, they can identify it with a positive, or wait, no, sorry. The false negative was 2%. The other one we want is the false positive, which is between 0.8 and 4. So we'll actually use 2% for both of them, right? So let's think about what I'm really saying there is a false positive means that I'm getting a positive test result even though I actually don't have the disease, right? So given that someone is negative for COVID, right, the probability that the test shows a positive result, so my false positives, right, people who don't have the disease but get a positive test result, this is actually about 2% or probably of 0.02, right? I think the lowest value they had in that range was 0.8%, so you could lower this down a little bit if you wanted to. Now, the probability that given someone has COVID, we get a false negative so that the test came back negative, the lowest value in that range actually ended up also being 2%. Right? So, you know, and like I said, there was a range of values there, so you could play around with them, but if we're using the lowest kind of value here and kind of one of the more common kind of middle values that we see here, you know, they're roughly the same. So if I'm thinking about something like, and then I said that probably, that somebody has COVID, if I selected someone at random at any given point in time, about 0.5% or the probability of 0.005 have COVID, right? Which means the probability that if I grab somebody at random, that they have a negative test result would actually just be the remaining 0.995. So you can think about it as if I gave every single person, if I had the capability of getting I'll move this, every single person in the US a test, right, then 99.5% of them would actually be HIV COVID negative, and 0.5% of them would be COVID positive if we could give everybody a test. All right, so now we might be more interested in something like, all right, I feel fine, but I get, I feel fine, but I go and get a test and it comes back positive, right? But I could be an asymptomatic carrier. Right? So given that I have a positive test, what's the probability I actually have the disease, right? So it's a little bit different than what we were doing up here, right? Notice that kind of they're in different order, and when it comes to conditional probabilities, order matters. Right? So I'm going to start writing this out in the context of that Bayes equation. So what we have here is my outcome of the test E and my state of nature 1 here. Right? So what I would do is I go back to that general form of the equation, We'll go back there real quick just as a reminder. Where was it? Right here. And just start plugging in my S1 and my E. Okay? So let's go. I did not like this because it wants me to go to slideshow first. All right, there we go. So here we go. All I'm going to do is plug that in or write that in the context of my example. So my S1, right, is a probability that someone's COVID positive times the probability of E, so the test comes back positive given that they're COVID positive. Oops. To save myself some room, that's the exact same thing I have as this first component of my denominator, right? But that was why we had that question of can I cancel it? Well, I can't, but it's the exact same thing. Right? Then the second part is the probability of S2. Well, if my S1 is COVID positive, S2 is COVID negative, times the probability I see E, this positive test result, given someone is COVID negative, right? Well, from here, it's a matter of plugging values in. So COVID positive, 0.005. Given that someone's COVID positive, what's the probability I see a positive test result? Well, I wasn't directly given that. Let me see if I can get this all on the same page here. Right? I was given that given someone's COVID positive, the probability I see a negative test result is 0.02. So if I'm conditioning on the same state of nature as I was up here, but looking at the different outcome of the test, what should this probability be? Huh? Yeah, right? Conditioning on the same state of nature, different outcomes of the test, this should be 0.98. I already said I know the probability someone's COVID positive is 0.005, right? Then the next thing is, what's the probability that they're COVID negative? And actually, I'm just going to blow this up. Oops. So we can just see what I'm doing here. Can I zoom out just a little bit? Nope. So now, what's the probability someone's COVID negative? If I move this guy and zoom. 0.995, so I'll plug that in. Given that someone is COVID negative, what's the probability they get a positive test result? Well, I go back up here. I actually had that. That was 0.02. So I plug my 0.02 in down here, right? And once I plug all those values in, we could actually figure out what this is. So I'm going to write out these in terms of the numbers. So we'd have what? 0.005 times that 0.98. First part of the denominator is the exact same as the numerator. And then the probability someone is COVID negative times the probability that if they are negative, they get a positive test result, right? Now it's a matter of crunching those numbers, right? I'm going to guess this ends up being close to 50%, but let's actually do the math. And I'll come back to this screen here in a second. If it helps, I'll leave this up here, but I want to go to just use Excel to be able to calculate for me. So I'm bad at this, but I don't like to use calculators at all. Because I make way too many mistakes with my fingers. So let's just use Excel as a calculator, right? 0.005 times 0.98 divided by 0.005 times 0.98 plus 0.995 times that 0.02. And this should give us the probability that given I see a positive test result, right, if I was just to go right now and get a COVID test, the probability that I actually would have COVID, right? If I'm thinking about kind of the whole public, actually it's not 50%, sorry, I was looking at this wrong. It's about 20%, right? Which seems crazy, right? But this is if you made every single person, regardless of symptoms or anything, go get a COVID test. Just because you see someone get a positive result, the probability they actually have the disease is relatively only at 20%. Right? Now, this is very different if we're talking about symptomatic cases versus non, but this is just if I made every single person in the U.S. get a COVID test, which is, I think was one of the things like, to me, or, if everybody rushes out the second they, feel their, left tricep twinge a little bit and think that they're dying because they have COVID, you know, we're going to have all these false positives, right? Because the majority at any one point in time, you know, like I said, I think I was looking at the data. I think I'm being generous here with 0.005. I think it was like over the last 7 days, roughly 100,000 people each day were new cases. So, you know, if I'm thinking about it lasts for 2 weeks, that's 14 days times 100,000. I'm at about 1.5 million, which is even lower than 0.5%, but it's around there, right? So, I mean, this is being kind of generous that if you make everybody rush out and go get a test, the majority of people don't have the disease. But if your false positive rate is as high as 2%, that's going to be a lot of people, right? If you make, if the 99.5% of people don't have it, that's going to be roughly 300 million people. 2% of that is 6 million people, right? So even if you perfectly identify everyone who does have the disease, that's only 0.5% of the population. It's the same sort of thing we talked about with thinking about these numbers. It'd be fairly similar to the HIV example. Just a little bit worse here because our false positive rate is twice as high, right? 2%. Now, if that is really as low as 1%, these numbers get better. But, you know, Bayes' theorem really highlights the issue with if you can't get that false positive rate to be really low, then just seeing a positive test result isn't super informative, right? So the idea is what we really want to do is make sure even if it's a really accurate test, like the HIV one, 99.9% of the time, if you have it, it identifies it. Well, that's great. But if the false positive rate is as high as 10%, well, now the positive test result doesn't mean a whole lot to us, right? It's not as high of a probability, right? It's not as indicative that the person actually has the disease. So, you know, I set these up in the disease ones. You know, we could do the guilty, non-guilty example. But really, if, you know, it could be something as simple as like, I'm interested in whether or not a company is earning positive or you know, earning above or below a certain amount of money. And I'm going to use different measures as indicators for that, right? So my test is like indicators of other statistics that companies are putting out is that giving me information about whether or not they're earning above or below a certain amount, or whether or not, you know, I don't know, whatever I'm, you know, concerned with how the company's performance is, right? But it'd be a very similar thing. It's just our tests, we're not thinking about it as like an actual administered test. It's more of like using something as an indicator, right? Or a proxy for what we're really interested in, which is the same idea here. We're really interested in the true state of nature, and we're just using this proxy, this best kind of indicator that we have, which is a test result of a non-perfect test. Okay. I think that will probably cover it for Bayes' theorem. We'll go over some of these, I think, fun little examples next class, and we'll dive into some kind of pushing our probability understanding a little bit further, relating it back to thinking now about variables, calculating means, and things like that. So, Excel and Connect assignment due by the end of the day today, so 12 o'clock or midnight. Other than that, should cover it. Any questions from me before we get out of here? Let's see. Oh, okay. All right. So that should cover it for us. I'll switch over, I guess, so you can kind of see me as we're leaving here. All right. So get those homeworks turned in, and I'll see you guys on Monday.